Hey guys, this is your video for the multiplication rule. So today we talked about some independent events. So just a reminder that two independent events are when one event does not affect the occurrence of the second event. Okay, so just kind of remembering that. The multiplication rule, we already have an addition rule. We call it the addition principle. And we use the addition principle when we were talking about the probability of A or B happening. And if you recall, that's the probability of A plus the probability of B, and we subtract out the overlap, the probability of A and B. Okay? So that's the addition principle. And the addition principle kind of goes along with that or statement. Okay? That helps us find the or. So what about and? So that's what we're going to talk about today. What about if we have two events, A and B? What's the probability of those happening? Well, instead of using an addition rule, we're going to use a multiplication rule. The tricky thing is that the multiplication rule is slightly different for if the events are independent or not. So we're going to look at the multiplication rule for independent events, and then later down in your notes, there is a multiplication rule for non-independent events. Just a slight difference. Okay. So here it is. Here's your multiplication rule. Kind of like the addition principle, I don't want you to rely on this formula too much, because you'll see it takes a little bit different form, especially when we have more than two events happening. So the basic thing I want you to remember with this formula is that this and symbol is usually associated with multiplication. That's the biggest thing I want you to understand from this formula. Alright, so let's do it. Let's look at this first example and let me show you how this formula comes into play. So we're talking about gambling here. A slot machine has 3 wheels that spin independently. So there you go. That is our kind of hint that these are independent events, the 3 spinning wheels. It says each has 10 equally likely symbols, 4 bars, 3 lemons, 2 cherries, and a bell. So I don't know if you guys are interested in gambling or not. I played around with it here and there, but I do use a lot of gambling in this class just to kind of, it's good for probability, but maybe if you do decide to gamble one day, you'll be educated. Think back to your stats class. Alright, so when you sit down at this slot machine, maybe you're thinking, what's the probability that I'm going to get 3 lemons? Okay, well, in probability notation, how we will write this, it will look like this. I'm looking for the probability. Of course, I need to define my event. Let's let L be the event that I get lemons. So what's the probability that I get a lemon, and then another lemon, and then another lemon? See, I'm using that and symbol here. So again, I know I only had 2 events, A and B up here, but look, I can be 3 events. It could be 5 events. As you see in a second, it could be 99 events. Okay, so that's why I don't want you to set by that formula too hard, okay? Alright, so there we go. So basically what the multiplication rule says is we think about these 3 wheels on the slot machine. On the first wheel, what's the probability that it's going to be a lemon? Well, the probability of that it's a lemon is 3 out of 10. Right? What about the second wheel? What's the probability that it's going to be a lemon? Well, these are independent, so it's going to have the same probability, 3 out of 10. What about the third wheel? Same probability, 3 out of 10. So what the multiplication rule says is to find this probability that I get all 3 lemons, I'm just going to multiply 3/10 times 3/10 times 3/10. 27 out of 1,000. And there we go, multiplication rule. Okay, let's keep trying some more examples. What's the probability you get no fruit? All right, the probability, let's let fruit be F. So the probability that we don't get fruit, remember no fruit, we can use our complement no fruit or not fruit. So the first one's not fruit, the second one's not fruit, and the third one's not fruit. So let's find that probability. I like to kind of put little 3 dashes to remind me of the 3 wheels. So, not a fruit. Okay, so a bar is not a fruit, so there's 4 that are not fruits, and a bell is not a fruit. So that's actually 5 out of 10 chance that the first wheel is not a fruit, 5 out of 10 that the second one's not a fruit, and 5 out of 10 that the third one's not a fruit, giving me, if I multiply, use my multiplication rule, 125 out of 1,000. Okay, next question, what's the probability you get 3 bells? So let's let B represent bells. So the probability that I get a bell and a bell and a bell. Okay, notice that there's only 1 bell out of the 10 possibilities, so that's a 1 in 10 chance on the first wheel, a 1 in 10 chance on the second wheel, and a 1 in 10 chance on the third wheel, giving us only a 1 in 1,000 chance to get 3 bells. I bet that's the jackpot. Very unlikely, about once every 1,000 spins on a slot machine will you get 3 bells. So what's the probability you get no bells? Okay, so we've already defined bells as B, so no bells we could say is no bell and no bell and no bell. Okay, so the probability that the first one would be no bell would be 9 out of 10, right? All the other 9 are not bells. Not a bell, not a bell, giving us 729 out of 1,000. Okay, see, not bad. Multiplication rule's not bad. Okay, last question. What's the probability that we get at least 1 bar? Okay, just kind of giving you, this one's a special one. This is a special phrase in probability, at least 1. Because I want you to think about, that means that at least one of them is a bar, meaning that, so let's let bar be R, since we've already used B. So let's let bar be R. So if we think about at least 1 bar, that means that in my 3 spins, one of them can be a bar, so that can be a bar, but the other ones aren't. But remember the order, that's not the only place the R can be. It could be in the middle, BRB, or it could be last, right? And that's just 1, like with 1 R, it says at least 1, so that could be 2, so it could be bar here, and then a fruit, right? Or a bar here, fruit, bar here. So what I'm trying to show you is that when it's at least 1, I have a lot of situations to think about and calculate their probabilities for. So a hint for doing at least 1 in probability is to think about it as not as at least 1, but 1 minus the probability that none are the bars. Okay, use the complement of at least 1. Okay, the opposite of greater than or equal to 1 is 0. That's the complete opposite. So let's do the complete opposite. Let's do 1 minus the probability of none. So as you're going through the rest of this probability unit, if you come across at the phrase at least 1, remember that it's easier to do 1 minus the probability of none. So let's try it. 1 minus the probability that none are bars. So no bar, and no bar, and no bar. Let me put that 1 minus in here. Okay, so no bar, so the chance of getting a bar is 4, so no bar would be 6 out of 10. Okay, which is 1 minus 216 out of 1,000, which would be 784 out of 1,000. There you go. Okay. All right. So one more quick example of of independent events is this baseball example. It says a perfect game is when a pitcher doesn't allow any hitters to reach base in all 9 innings. So historically, pitchers throw a perfect inning, an inning where no hitters reach base about 40% of the time, and there's a link to where that came from. So to throw a perfect game, a pitcher needs to have 9 perfect innings in a row. What's the probability that a pitcher throws 9 perfect innings in a row, assuming a pitcher's performance in an inning is independent of his performance in other innings? So we're assuming it's independent. Okay, now, so if we think about it, let me start with calculating it. Basically, it's saying there's a 40% chance that they have a no-hitter. So I'm thinking about 9 of these little spaces, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And the probability of each of them being a no-hitter is 0.4, right? So a quicker way for me to write that would be 0.4 to the 9th power, right? So that is totally fine. And back up here, you didn't have to say 3/10 times 3/10 times 3/10. You could say 3/10 cubed, and that's fine as well. Okay. I just like putting the blanks because it helps me kind of think about them as separate events. And then, of course, it would be hard to do the probability notation, like you would be saying, like if I let n be a no-hitter, then that would be n and n and n 9 times. So it's totally, this might be one where you just kind of write it in a complete sentence, saying the probability that a pitcher throws 9 perfect innings in a row is 0.4 to the 9th, which equals, can't say that, I know that off the top of my head, 0.123, yeah, there we go. So not a very large chance, big chance. So when you see people having a perfect game, pitchers having a perfect game, know that it's not very often that happens. Okay. Moving on to non-independent events. So this is when one event happening affects the probability of the next thing happening. So the formula looks crazy hard, but it's definitely not. So I'm actually going to come back to the formula after I've done a quick example, okay? So this example just, kind of boring. We've got 10 marbles in a bag. 3 are red, 5 are blue, 2 are green. We draw 3 marbles from the bag without replacement. So very similar to the slot machine. The only difference is the slot machine, the 3 wheels were independent. But here, the marbles are not independent because once we take a marble out of the bag, we're not replacing it. So since we're not replacing it, it affects what's left in the bag. So that's going to affect the next probability. Okay? So let me show you. It says, find the probability that all 3 marbles are red. Okay, so let's let red be R. So the probability that I get a red and a red and a red, just like before. Okay, setting it up. I know I'm going to be multiplying. This is still multiplication rule. So here we go. It says the probability that all three are red. So I draw a marble out. What's the probability that it's red? Well, 3 out of 10, right? So I take that marble and I set it aside. So now I can't put 10 under here because I've taken a marble out. So now I'm down to 9 marbles. And how many of them are now red? Well, the first one was red, so there must be only 2 left in the bag that are red. So I take that one, set it aside. Now there are 8 marbles left in the bag, and only 1 of them are red. Okay, so it's a very, you got to think about, okay, one affected the other. So what is this formula saying? It says, okay, this A represents picking a red marble, okay? So I'm going to take the probability that it was a red marble, which was 3 out of 10. Now this second one says, okay, given that the first one was a red marble, what's the probability that the next one's red? So see how that conditional probability notation, that's all that means. Like, okay, A has happened. I'm given that A has happened. So now what's the probability of B? Since they're independent events, I know that it not independent events. I know that it matters that A has happened. It's going to affect B. And it did. So since the first one was red, I had to adjust my second probability to show that because the first one was red, now the probability of the next one being red was 2 out of 9. And then I had to do it again. So now since the first one was red and the second one was red, given that those two have happened, it affects that the third one was red as well. Okay, hopefully that helps with that. Please don't memorize. I mean, it's good to know it and have it handy, but you don't have to use it to be able to figure out these probabilities. All right, let's let B be blue. Let's do the next problem. It says, what's the probability that none of the marbles are blue? So the probability of not blue, and not blue, and not blue. All right, here's my 3 draws out of the bag. The first draw, I'm thinking, okay, what's the probability that it's not blue? Well, that's going to be 3 plus 2, 5 out of 10. I take that marble, set it aside, and I say, okay, now I have 9 marbles left. The first one was not blue. What's the probability that the next one's not blue? 4 out of 9, because I've already had one taken out that was not blue. Set that marble aside. I'm down to 8 marbles in the bag and 3 of them left that are not blue. Okay. The next one, at least one. There's that phrase again, at least one. Remember, I should think about at least one is 1 minus the probability of none. Okay, so at least one marble is green. Let's change this question to be 1 minus none of these marbles are green. So not green, and not green, and not green. So not green would be 8 out of 10. Set that marble aside. Now I have 9 marbles left, and 7 of them are green. Set those 2 marbles aside. I've got 8 left in the bag. 6 of them are not green. So whatever that math is, I'm not going to actually type it in the calculator, but whatever that math is would be our probability. And the last problem, what's the probability that the first green marble is the third one drawn? Okay, so that means that the first draw is not green. And the second draw is not green, but the third draw is green. So let's take this one at a time. So I reach in the bag. The first marble is not green. So the probability of that would be 8 out of 10. Put that marble aside. Now I'm left with 9, and 7 of them are not green. Set that marble aside. I've got 8 marbles left in the bag, but the third one is going to be a green marble. So how many greens are left in the bag? There are 2. We haven't drawn any green ones yet. So it would be 2 out of 8. And there we go, the multiplication rule. We will practice some more of these. Please bring your questions as always. See how I can help or fill in any gaps that I didn't cover in this video. See you in class.